Okay, we can start.
Are you sure it's recording? Didn't get any message.
Outside from the
Okay. All right. So I'm going to talk about fair data and ALF, how those two things are fit together now. And I could not have done that, or most of the work has actually been done by Jonas with us and Pizarro from FAIRmat. And this the subject of this talk is, of course, a bit new for some of you. So I'm going to start, before I truly start the talk, I'm going to explain the terms so that you have an idea of what we're talking about. I'm going to go in more detail, but in really short words, so that's not precise, not complete. When you talk about data management, is what we do already anyway if you produce data, right? So you produce data, you copy it from somewhere, you analyze it, you save a part of it, you make some backup. All of that is data management. But when we talk about data management as an area, we are of course talking about doing that aware of what we're doing, usually with some plan, so a data management plan, which means that you take those steps consciously of what you want to achieve and how you want to achieve it, right? So that's a key concept here. And we actually, in this context of research and in this context of open science that we do, we are really interested in the so-called FAIR data. I'm going to go into more detail later on with what FAIR data stands for. But for now, you can just consider, link this name, this word, this expression to data that you can use. So data that is open and that you can use. People can get this data and do something with it. Okay, so fair data is data that's open and usable. NOMAD is our partner. It's trying to make our data fairer, and it's just a repository for material science. Okay, it's more than that. I'm also going to say more detail, but the key point for us is that they are a German an institution that is doing this work, and it's been very nice to work with them, so it fits our purpose as well to get our data into the repository. ALF, I don't need to explain, is our code for quantum Monte Carlo. Okay, so with that explained, so fair data is usable data, and data management is what the name implies. We can actually properly start. So my plan is to first explain why I have this work, why am I talking about that, why to work about it at all. Then finally explain more detail what is the fair data thing. And then very briefly talk a bit about NOMAD, talk a bit about ALF, and then come to how is our work together going along. It's going along well, and what the outlook is at the moment. All right. So the main reason, the fundamental reason of why you should care about data management and why you care about making data fair is that data is valuable, right? It's expensive to produce. Sometimes some of the data is unique. And here I collected some examples. It's just some examples. I'm not trying to be representative, let alone complete. But one nice example is the 2004 Nobel Prize for the top freedom of the strong interaction. It's a work that in part was based in some reanalysis of some accelerator data from the 80s. That's from an accelerator in Germany, actually, and that was instrumental for them to produce their results. Another example, which also happens to come from the high energy physics, is an article published this year, which used data from Telecom in the US, which closed more than 10 years ago. And they reanalyzed this data and claimed to have 7 standard deviations data implying physics beyond the standard model, right? It's received a lot of attention. I'm not right now on top of it, so I don't know if this lots of attention is positive or negative, but this received a lot of attention. And it was only possible by having this old data. And outside of physics, of course, essentially any area that cares about a system, a field that changes with time, that's not completely static, benefits from old data. So I'm not gonna cover all the examples listed here, but astronomy, for instance, is an obvious candidate, right? Observational astronomy in particular is essentially built on historical data. Anything that's the most interesting stuff is about changes in the sky, and you can only see if change happens if you have all the data to compare it. Biodiversity is the same, or biology in general. One of the key subjects nowadays is, of course, the loss of biodiversity. Species going extinct, and well, we can only tell how they are doing if you have time series, if you have old data. One concrete example is how they found. They managed to find and to rescue some data from 1906 about the vegetation in the Swiss Alps. And with this data, comparing with data taken 100 years later, is that they were able to claim, with some good foundation, that indeed this vegetation had moved upwards, which is yet another sign of the climate warming, which brings us to climate. Of course, all these studies in climate depend on historical data. You don't have models if you can climate models if you can train them, if you can test them against historical data. And here also there's a nice concrete example, the ice cover. The oldest image of ice cover we have is a result of a lot of luck and a lot of work by a number of people who found in some storage room in NASA some old tapes from the first satellites that have taken pictures from Earth, and they were essentially there forgotten. And of course, you have to go through a lot of effort to rebuild or repair old machines that could read those tapes and program new software that could essentially reverse engineer and get the data out. And they got very interesting data, higher resolution than what had been stored of the analyzed data at the time. So it was really valuable. And it's so on and so forth. The list goes on. And that's the point of fair data, of managing your data properly. You don't want to have to rely on a lot of luck and have to spend a huge effort to get access to this data that was produced, that was paid for, right? You want it to be available for as long as possible because it is valuable. So that's the key reason. If you're doing research, you will care about science. And if you care about science, keeping this data accessible is important. So what are the advantages of data management? So the first one, proper open data management. The first one is enabled fair data. You cannot have fair data without managing your data well. That was covered in the previous slide, but it's not the only advantage. You also have, currently science is going through a replicability crisis, as they say. It started with psychology a couple of years ago. Some groups tried to replicate the results of some dozens of important papers in psychology and failed to reproduce more than half. At first, the so-called hard sciences were a bit smug about that. I always knew that it was not really so serious. But when they did the same with chemistry, biology, some other fields, the results were not much better. So we have a really difficult time replicating previous research, and to a large degree is because of missing data. It's not so simple. You also miss workflows. You miss software. There's a lot to gather data, but this environment is included in the efforts to have fair data. So replicability is a serious problem. It's really important to solve, and fair data plays an important role in solving this. We also must, of course, have the data there. You don't have to do it again, right? It's linked to yet another crisis, so-called bias problem, which means that we only publish positive results for a good reason. You want to look good. You think that negative results are not relevant, but this is actually bad for science. It means that whatever you tried and did not work, someone else is bound to try again in the future and again. So it's really a big waste when you don't publish your failures as well. So to avoid duplicate efforts is also important to keep your data available. The previous slide had a couple of examples of how having historical data, having old data also supports new discoveries. It's not only about reproducing, it's not only about avoiding waste, it's also about finding new things. Sometimes it's very, very helpful to have them, it's very important to have them. A side effect that should not be forgotten is how it facilitates collaboration, right? Especially if you have a large amount of data. Sometimes to collaborate with people off-site is hard because, well, You have to put it somewhere. And if you are doing data management, if you have already your data in some repository, you just have to give them the link to this repository. It's done. They can also analyze. Another one that should not be forgotten is that all these reasons are not new. They've been known for a couple of years, and funders are behind, but not completely behind. So they've started also, both in the US, in Europe, and elsewhere, to demand that you do proper data management. Right now, their demands are set at very low bar. So little more than a data dump is enough to satisfy what they're demanding, but the tendency is that it becomes more stringent, that they want proper data management with time. And the real question is, I mean, if you're going through the trouble of producing this data, if you have to manage it anyway to some degree to fulfill this requirements, then why not do it properly, right? So that's another point. And there's a last point that might be interesting, which is estimates are that papers which have their data shared receive between 10 and 50% more citations. Now, of course, again, estimates, right? It's you do some you have to take some assumptions to make that. And especially the higher end of this scale, the 50%, is probably, this is true for some area, it depends on the area a lot. And this is particularly true for areas like astrophysics, where you probably should see it not as a plus in citations if you have your data in a repository, but as a minus if you don't, because actually it's part of their culture to have this data. So if you don't have this data, you are less likely to be taken seriously or to be considered. But the advantage is always there, as long as, and that's an important thing, your data is available in a repository. That's the thing. So it's not enough to get your data and put it in your personal web page at the university. That doesn't cut it. It has to be in a repository, otherwise this effect is not observable. So now that we know why we're doing that, let's take a look at what's this acronym, because FAIR is actually an acronym, what it means in a bit more detail. So again, the bottom line is that the data remain usable. That's what we mean by that. That's what we want to achieve in them. And the steps that the community have come to believe that are necessary to satisfy that are given that it's 4 letters, where F stands for findable. For data to be findable, it is first have to have a unique global ID. It's essentially, you should be able to refer to it in a way that everyone knows what we're talking about. Hey, I'm talking about data X, Y, Z. And it should be clear what is that? What data is that? It should not depend on where it's stored or any other factor. It should be a unique ID. And second, and that's extremely important, it has to have a rich metadata. What does it mean? It means that it's not just a data dump, right? If you have 50 gigabytes of Conte Monte Carlo data somewhere, so what can someone do with that if you don't have any other information? That's completely useless, right? So you have to include as much information as possible so that someone, let's say, Googling for your data, okay, Google, Caroline, whatever, manages to find your data. So the more information you include, packaged together with your data, the more findable it's going to become. And everything I say from now on in this slide applies equally to metadata as to data. Both are equally important because data makes no sense without metadata. Okay? So again, it should be findable. You should be able to Google it, and when you find it, you should be able to tell people, I'm talking about this, this data. Second, it should be accessible. The same in this picture of Googling for something, it doesn't help to find something, click in the link and find the 404 page not found message, right? It's obviously useless. So it should be permanently retrievable. You should be always available. You should be able to truly get to it, right? Of course, that's ideal. Nothing is eternal, but you should try for it. And it should follow standard, open, free, well-known protocols. I mean, HTML, whatever it is. It should be something you don't need a special software, let's say, to access. So there should be no barrier. It's essentially like saying, okay, so you Googled it, you found, you click on it, you came to it, it's really there, and now you should be able to download it. You should be able to open it without trouble. The I stands for interoperable. which essentially means that let's say your data is numbers, so there should be some table like comma separated values if you want, or XML or JSON or whatever it is, but something that's formal, so not just some scribble, say it anyway, or a picture of lab notes, whatever. It should be a formal language, a proper defined language that is known and accessible and free and so on and so forth. It's again, if you keep the picture of finding the data, downloading it, being able to open, you don't want to just see something that looks like a binary file. You want to see the numbers there, and it should have qualified reference, which is essentially having, I mean, part of it at least is having it linked to as much as possible. So if it's data that's being used to produce results that that are published in a paper, it's good to have a link to this paper there. If it's numerical data produced with a given software, it should be limited to the repository where the software is found, and so on and so forth. I apologize. In the last slide, it stands for reusable, which is essentially the whole purpose of this effort. And then we come again to rich metadata. It's been mentioned before, I emphasized it enough, but it was about finding it, right? You want a given system, like a tunnel or whatever, you want to be able to find it. But if once it comes to actually using it for something, let's say you want to compare your current data to some data that's available on the net, you want to be able to do something with it, like plot perhaps some points together with yours so that can make this comparison in a graphic. So you should have all the information necessary for doing that. So you should know what are the columns, you should know what's the temperature that's relevant, you want to know where it came from, when was it produced, and so on and so forth. Again, as much as possible, you want to have all the information so that you can actually use it for something. And once again, follow the standards as much as possible. So if in your community, things are usually plotted or stated in a given way, try to do that, right? Try to respect it. Under the principle that as little surprise as possible, you want to give to people trying to use your data. Right? They should be there, and if they expect something to be in a given way, if at all possible, make it this way. Okay. You can read in much more detail elsewhere, for instance, in this paper. That's where I based this slide. So that's fair data. Data that you can use, that you are really careful to try to make it usable in the long term. Which brings us to NOMAD. NOMAD is, there are many efforts, many similar efforts elsewhere in the whole world, but they are doing a very good work. They're putting a lot of effort, and they have the funding for that to try to be the go-to place for materials data. Okay, so this is their landing page. If you Google for a laboratory, you're going to come here. And then they try to make it as easy as possible as well. So if you have data that they can accept, you just click and upload. You're going to be taken to a page where you can drag and drop or find the file you want to upload. There are instructions there. There are tutorials. There are video tutorials. So it is relatively easy. Actually, it is pretty easy to just upload your data. And once it's uploaded, what does it do? It's used the metadata that is expected, that should be together with your data. They only accept it if it has metadata. A minimum of 7%, and they populate fields internally with this metadata, making it possible for you to search here in a very nice way. And once you find something that you think you might be interested in, they display this data for you in a very interesting, in a very helpful, in a very useful way. They even go as far as offering ways to analyze this data without even downloading it at all, just using their own servers. Okay, we're not there yet, but it's a really nice feature. We might make this in the future. They started off with a lot of DFT simulations on material science. They have upwards of 100 million data sets, I think, or data from 100 million plus calculations, and besides these calculations, they also have started expanding some time ago into experimental data. It's a challenge, right? Different labs have sometimes custom-made equipment. They have, every group has its own way of saving their data and so on and so forth. But they moved along. They have some nice progress on that. And lately they've been trying to include in their data also quantum carbon, and that's where we come in. We're actually one of the first groups, one of the first softwares that does quantum carbon to be included in NOMAD. And on the one hand, it means a lot of work also for us. So we have been iterating and coming to them back and forth for some time. In particular, to define this metadata in the so-called schema for how this should be done properly. And on the other hand, this of course gives increases our profile page, right? It's nice that we are doing that. That ALF is the software package helping them putting it into the fair data world. ALF, I don't need to come into detail. I guess all of you know it's our quantum Monte Carlo package. It can simulate general hyperthermals with a lot of flexibility, with high performance. It's not that difficult to use once you get used to it, and it offers lots of advanced features. So both together, you see, ALF is about those simulations that have an important point of application, solid state physics. So that's the point of contact. And NOMAD is an important repository. They are more than a repository, I should say. They have the repository, they have what they call archive, they distinguish both. One is for raw data, the other is for data not so raw. They also built an encyclopedia out of it. So using those sets, they try to make encyclopedias of whose entries are, for instance, materials. So you have all kinds of, if you click in silicon, you're going to have all kinds of information about this automatically to a large degree built from this data that people from everywhere upload. And I hope it's now clear that it's advantageous to both ALF and NOMAD to work together, right? We have in particular, so for NOMAD, of course, they want to expand into quantum Carlos, so for them it's obviously a nice idea to include ALF. And for us, we have for some time claimed that ALF is very good for producing golden benchmarks and standard values. And it's true, it is good for that. But if you look for such data, it does not exist yet. No one went through the trouble of really producing this data and making it available, that someone could use, okay, that's the standard. Someone invested $1 million, 4 hours of simulation into that. This is really hard to beat, it would be expensive and so on. So let me get this data to use as a data comparison, for instance, or whatever I want to do. Once this integration is complete, we're gonna be in a position to do that very easily. Or someone else wants to use all to do that and get citation for their data. So what's the step? So where are we in this integration? I think the best way to show that is to share with you some screenshots from our work in progress. Of course, parser and schema. The parser has been written by Jose, as I said, from FAIRmat. FAIRmat is the institution behind the NOMAD, making NOMAD go forward, and Jonas is with us. He essentially wrote single-handedly the schema based on input from everyone. It's true, but thank you very much. And the way it looks right now is a bit like that. So that's the page you get when you try to upload your data to NOMAD. And what's nice here? I don't know. Does it have a laser?
Yeah, the red.
You have a list.
Okay, cool. So here I have ALF. That's really nice to see. If you go now to the NOMAD page, you're not going to have ALF because this is in development, of course, so it's not yet there. But ALF is here, and you can actually upload your data. For those familiar with the file structure of ALF, you're going to see some nice familiar things here. Of course, as written here, I don't know how well this thing, but that's data. .h5, it's the main file with essentially all the results. Then I have info about it, with information about the run, the configuration I finished, and the input parameters file. So it worked. Below here, I didn't include in the screenshot, there was a success message. So it works. And If you look at the overview of the information it gathers from this data example here, it looks like that. So you have component card as an apple name. The problem is ALF. It's of course for material science, so it expects a material, and we're simulating a Hamiltonian, right? But the solutions so far talk about materials that have X or and 16, which means it's a lattice of 4 by 4. We have 16 sides, right? All of that is still work in progress. Of course, all of that can be improved or changed. We are working on that. It might be the solution, or we might come up with something else. It's of course 2D. They don't have 2D materials, but a solution that I found pretty fitting is called the quasi-2D. Yeah.
Well, the NOMAD will not say Hamiltonian is the material at one point. Are they going to stick to their nomenclature of material?
I don't know to which degree they can be flexible. I don't know. We have to talk to them.
Because it's sort of ridiculous, right? I mean, honestly, it's a bit ridiculous to say that it's. I mean, of course, Hamiltonian is a material in ideal sense, but you're weird. It's weird.
Yeah. What's it built with? It's made of rubber.
Was it now is not person capable of saying we have to adapt our NOMAD to be able to look at simulations?
What we see here is a mixture of characteristics of their software that are superficial with characteristics which are deep. So the superficial ones he can change for us without problem. And this might be one of the deep ones that you have to talk to other people. But I'm guessing here. But that's certainly the sort of stuff. That's one of the reasons I'm presenting it here in the group, so that we can discuss that and see what's the way forward. But we do have already the lattice information is properly here displayed. They have a picture that for us doesn't bring much, but once it's a more interesting lattice, it does add to it. The need of a unique ID is automatically fulfilled. Here I have the entry ID. So it's a collection of characters. And this, as I said, is the overview. By the way, you can click on the one in encyclopedia.
But can I still ask a question? I mean, so they have a standard to define a crystal structure, right? So they must be much better than we are at defining lattices.
I think with that we came together already. I think, right?
So do we have? I mean, there are tons of there are standards for lattices. I forgot the names of that, but then you have the point group, you have the translations, you have the public, So
we've discussed that. This is the first. That's just the first draft. We talked about that. Yes, we believe that we can map 1-to-1 in a nice way. So that should be done.
But will they give us their standard and we have to adapt to it because they should be more, we just do very simple stuff compared to what they have. I mean, they cover all the possible materials. So they must have tables of all the possible. They must be able to, how many grounded lines do we have in 2, right? 3, 4. Right. So I mean, we don't, so they must think in that way, right? In terms of real crystallography. And so what we want to adapt to that. You understand what I mean?
Yeah, calling our lenses according to the usual crystallographic names. Yeah, we can do that.
Okay.
I think that we probably have no data than just the crystallography. Because, for example, we can at least
we have the orbitals.
Some defects in the lattice, or we have complicated interaction. And I think for interaction,
well, we
don't have any.
Well, we have there's particular things. There's the interaction, there are defects, which weight the symmetry, and there are just the basic calculations which are based on a Bravais lattice with translation symmetries and also some type of point. Right?
We have like a large class of of our models that can be mapped, should be easily mapped to their nomenclature. I mean, we still have, like in principle, we have a bigger freedom to basically put everything in one unit cell and don't have basically any private letters left. But I guess we can map at least a large subset of our models onto something that should be one level mappable to their nomenclature.
Okay.
Yeah.
So so at some point we might have an entry in the encyclopedia for, let's say, word or whatever it is. Right now, what we already have is that we can click into the data information, the data that's uploaded, and what we see here, if it were dynamic, you'd have first this column, and then you choose on what you want to click, which information you want to access. In this case, we're getting the calculation one, and then I have all those measurements. If you click into the green function, the table time, you obtain that here. It might look a bit strange, all of those dimensions in that, in case you can read this 213 times 1 times 1 times 1 times 16 times truth answer. That's just the number of things of your quantum curve, number of orbitals, again orbitals, the time slice. The 16 is the last side, so you have one data point for each site. And I believe the two at the end is to store the real and imaginary part of the correlation. And if you click on it, you can just see it as a table there. Right? So it's surely there. And when you talk about parsers or parsing information into the repository, that's what it means. So the information that's just there in the file you upload is being translated into this user interface. Another example, you can go to Monte Carlo and see that, okay, you're simulating the Hilbert model and you want to see what's the strength of the interaction. So you just click here and then you got, I don't say number here, but you have to say it's ability. All right, so what's the outlook? We're here. What do you expect and want to achieve? This year still, we should have a finished first beta version. Possibly, maybe I'm being optimistic here. Jonas is taking care of our local version. He can tell us better about that. But maybe we can have a beta version working locally until the end of the year. Here's something I forgot to mention. NOMAD is a federated, so-called federated repository. What does that mean? There is indeed a central repository where you're going to have your more refined data uploaded to, but the truly raw data, really terabyte wise data, that's supposed to be kept locally. So we're going to have NOMAD is open source. You can install, you can run it on any server you want. And we have an instance of NOMAD running right now here at our university. And so the idea is that you upload your raw data to the local instance, and you have a refined data at the central one. So in the now local NOMAD, it's called NOMAD ACES. We expect to have a parser working. So we're expected to be able to accept alpha data still this year. And for that, of course, we have to make some small or not so small adjustments to the output of alpha. Some of them are really trivial, like including the name of the program, the version, commits, whatever you want. Some of them are easy. Some others might mean some restructuring, but it should be all doable, at least in part. How are we going to get this year? For over the course of the next year, we should have hopefully, or more than hopefully, we should have the ALF parser at central NOMAD. We should be in a position to finish adjusting our output so that it really fits there. The parser should be improved, and as software developers, people have ideas on how to improve it and what they'd like to see. These are going to be hopefully at least partially implemented. And who knows, we have PyAlpha already, which is this Python interface for ALF. If you could get that somehow into their analysis, central analysis, that would be really cool, because we can do some advanced specific analysis for our solid data with PyAlpha. So if that were a bit there, that would be really great. Okay, and that's it. Thank you.
Thank you very much. When we continue to,
I guess you can stop the call.
huh?
I guess you can stop the call.